Hey guys, and welcome back to the series. This is going to be yet another format of video. I won't be coding anything live today, there's a lot to cover, so instead I'll be talking you through the changes that I've made and how you can take this and run with it. If you haven't seen my last video that explained the theory behind multi-objective, I would strongly recommend you watching that video first, which you can check out here. And if you're new to this channel, this is our 8th video in the series, so if you want to follow along from the start, you can do so here. This video is going to cover converting our existing GA to multi-objective. To do it in the nice, correct way, involved a lot of refactoring. I'm really sorry here, I know you guys like to follow along, but I don't think that it will be possible for this video. To help ease the pain, I've included an updated repo down below that has had some serious overhauling. So I'll go through the changes in this video, but I strongly recommend grabbing a copy of the new repo. Before we start, I have to give a disclaimer. I know that the way that I've written a lot of this code is not the most efficient way. It's written like this because it's quick, it's easy to follow, and it's easy to test. That said, the ranking and crowding distance methods have a lot of room for optimizations, and I'm not going to go through these optimizations in this series because that's not really our goal. But if we get to the end of this series and you guys want me to cover them then, I can. However, I think that these techniques are better saved for our next series, where we will be taking all of the concepts that we have learned here and making a generic GA. That is right, we will be writing a genetic algorithm framework that we can relatively easily reuse in other projects that we might have. Now, if you are determined to optimize our existing code, first up, I love the motivation, but be careful. This is incredibly easy to make small mistakes while doing this, and they can be really hard to track down. Trust me, I work with GAs for a living. But if anyone wants to, I've included a number of test cases which you can use to test the validity of your GA as you make speed improvements. We'll talk more about these test cases a little bit later. So let me show you the end result, and then I can talk you through what has been changed. So hitting run like normal, you can see our example with 10 towns, and nothing seems to be different. But hitting the spacebar brings up a new screen displaying our individuals on our fitness graph. Now you probably notice a few things straight off the bat here. One, the colors. So each color here is a unique rank. So there's 15 or 20 individual ranks here at the moment, and they all have their own color. The more blue they are, the lower their rank. Number two, the next thing you might have noticed is the strange jumps that the entire map of individuals is doing. That is us renormalizing our fitness values. As the values can improve a lot after the initial spawn, some ongoing normalization is needed to actually see the improvements. Otherwise, the entire population would look like a single dot. Number three, you are probably saying, wait a minute, you big liar. There are a lot of generations happening right now, and you said that all of our individuals would move onto the first front. And now, while this is again technically true, there are not enough feasible yet unique results for this problem that would allow every individual in the population to be both unique and in the first front. And that brings us perfectly to the last thing that you might have noticed. There are no individuals with duplicate sequences. Yes, I have overloaded the equality method of our individual to check for a sequence when comparing if they are the same. Yes, it is slower, but I've multi-threaded the simulation so it isn't a big deal. Wow, okay, so I'm sure some developers must be grinding their teeth at that comment, but nevertheless. Oh, and I forgot, one last thing. You can see that the path being displayed is jumping all over the place. As we no longer have a fittest individual, each update, we randomly pick an individual from our first front and we show it. After all, they're all equally fit, technically. So before we get into the actual ranking and crowding distance code, I want to go through a number of the changes that I've made to A, visualize the Pareto fronts, B, facilitate the performance hit that we're about to take, and C, make the code more manageable and testable. So for those of you who don't know, this repo was originally a game template that I had written for some fun little side projects. And when I started this series, I grabbed a copy, deleted everything I didn't think I would need, and kept the bits that I did. When doing so, I removed all of the logic that I was using to have multiple screens. So I've just dumped that back in the repo, and that starts with the Screen Manager class. So our Screen Manager class is surprisingly simple. It has a list of screens, and a reference to our main window. We can then add and remove screens from this list. When we perform our update, we will loop over each of the screens, and if their update flag is set to true, we will call their respective update method. The same thing is true for the draw method. Now, some of this is probably overkill, but keep in mind this was intended to be used with a 2D game with menus and whatnot, and I thought that you guys might like to repurpose this project, so why not? One thing to take note of here is that we are drawing screens on top of one another, so the order that they are added to this list is important. Also note that our add screen method inserts a screen at position 0, indicating that it would be drawn first, so it's drawn on the bottom. Great, so jumping over to the game class, we've added a private member variable called Screen Manager, and we are instantiating it in the constructor. Then, in the main game loop, where we were previously calling simulationscreen.update, we now call screenmanager.update. And where we used to call simulationscreen.draw, we call screenmanager.draw. It's that simple. Now that we have multiple screens, I've gone ahead and made a new Pareto visual screen class. So the entire purpose of this screen was to provide us with some feedback so we can see that our code is working as expected. In the constructor, we first grab a reference to our population. We will use this to update the visuals based on the fitness values after each generation. We then create the list to hold the visuals, one for each individual. These are the colored dots that you saw previously. We then populate the visuals. We'll keep them in memory and update them on each frame rather than create them new to minimize overhead. We then create our graph that we will show the individuals on. So other than that, this screen only has two methods, update and draw. Update looks at the current population, creates the adjusted normalized fitness values for each of the individuals, updates their position, and colors them based on their rank. The normalization being done here on the fitness values probably deserves a minute of attention. We are actually stretching the population on each axis between the values of 0 and 1 for graphing purposes, where the most fit individual in each objective will have a fitness of 0 and the least fit will have a value of 1. Then we have our draw method, which is pretty boring. We print our border, we print our graph, and we print our individuals on the graph. This is probably a good point to mention a helper method that I've written that you can also use. In our front visualization helper class, I know my class names are the best, there is a method called showPopulation. This method takes in a list of individuals and will create a window, calculate the normalized fitnesses, and populate a graph based on the population that you passed in. So if you ever have a need to visualize your population for debugging purposes, you can use this. Oh, and exiting is the same as the main screen. You can press Q or escape. The next change that I have made is making the application multi-threaded. So everyone knows more threads is equal to more faster, but why specifically have we done this? Well, we've set the refresh rate of our screen to 60 frames per second. That means that our screen is not only drawing 60 times per second, but it's also checking for user input 60 times per second, and it's updating our path 60 times per second. Or is it? Well, in the previous video, I added a generation timer to run one generation every 0.2 seconds. So that's once every 12 frames. So if we run a generation and it takes us 0.1 seconds to run, our screen can't draw or update in that time. So if you press a key to move the camera, there's nothing running to check that input and the simulation becomes unresponsive and laggy. What would be great is if we could start our GA running, but in the meantime, keep refreshing our screen. Remember that the path shown on our screen doesn't need to be updated until the current generation has completed. So in the meantime, we might as well keep our simulation showing the previous path, checking for user input, and remaining responsive. Great, so we can do that pretty easily. When we come through our loop, if 0.2 seconds has passed, we can start the generation on a new thread. And when it finishes, we will update the path. But now that we've made it multi-objective, it's taking longer to calculate, 0.5 seconds. So let's take a look at what would happen now. We would start our simulation, and then we would start a generation on another thread. But wait a minute, before that generation has completed, the 0.2 seconds would pass. So we would start a new generation. So now we have two that are running on top of one another. So who knows what the outcome would be? It's likely that some exception would be thrown somewhere. So what do we do? The first suggestion might be raising the minimum generation time from 0.2 seconds to 0.5. Or maybe if we want to play it super safe, we could make it 1 second. But you really never know what the worst case runtime could be for this. What if someone cranks the number of individuals in our population way up, or runs our code on some really old PC? Well, we'd be out of luck, and in general, hard coding it to some value is really bad practice. So instead, what would be great is if the packet of work we send off to do the generation could tell us when it's complete. That way, we could set our minimum delay to 0.2 seconds, but only if the generation has completed. Coincidentally, in C#, this is incredibly easy. A packet of work is called a task. Now, if you aren't a C# developer or you aren't familiar with tasks, they allow us to run a chunk of code on a given thread. Now, that could be our current thread or a background one, it doesn't really care which. It also has a flag on it to indicate if it's finished running or failed for some reason. So great, this is exactly what we need. Jumping back to our game class, we've added a task as a member variable and called it doGeneration. Then, in our main loop, before we do a generation, we want to check if our task has completed yet. If it has, everything that used to be inside the if statement should now be done as part of this task. The syntax here might be a little foreign, but it really is that simple. This will start our generation running on another thread, and once it's done, the isCompleted flag will be set to true, and the very next frame, assuming 0.2 seconds have passed, it will kick off the GA running again. There is one very small caveat here. While our generation almost runs entirely independently of the visualization, the update sequence call updates a variable that is used inside the simulation screen class called pathlines. Since pathlines is the list of lines we're showing in the visualization, if we don't put a lock around accessing it, it's possible that we could try and update it while we're also trying to draw it at the same time. Again, this is a really small chance, but not one that we want to take. In C#, this again is also pretty simple. We can just wrap access to this variable in a lock. We then need to do the same thing for our total distance string variable. Next up, we have our very large refactor of the world class. Now, I'm sorry, I tried to avoid this, but it was really needed and was done for a few reasons. So let's take a look at an example method that we have shifted to our new static world helper class, spawn population. The code used here to spawn a population is not necessarily unique to this one problem that we are solving. It is simply generating a population of individuals that have a list of integers as their genome. I can personally think of 3 or 4 projects of my own that have an identical encoding. So if I was to use this code elsewhere, why would I rewrite it when I can just reuse it? This is ever so slightly starting to follow some of the principles that our generic GA will follow. These methods are bordering on functional. Given known inputs, we should get some known expected outputs. This has a side effect where some things aren't done as efficiently as they could be, but it's really easy to follow and lends itself perfectly to creating test cases. Speaking of test cases, we now have a project in our solution for our test cases. Writing various methods of our GA using static methods allows us to very easily create test cases that cover the majority of our GA. Now, our test cases here have been broken down into 3 classes. The first and largest is the generation tests. This contains 8 methods that each test different functionality in the generation component of our GA. I won't go through all of them now, but let's take a look at our method ensure ranked tournament selection test. The purpose of this test, if it's unclear from the name, is to ensure that our tournament selection is working with our new multi-objective ranking system. That's not a super trivial thing to check, so to help that, I've created a method called getTestPopulation. Looking inside that, we can see that we are hard coding some individuals. So let's get those up on a map and see what they look like. Awesome, so from this we can see that A, B, and C should all be on front 1, D, E, and F should be on front 2, and G should be on front 3. Back in the generation tests, once we have our population, we call our static update population fitness method. Again, this is the same method that our GA calls as it's running. Once we have calculated the fitness of our individuals, we can grab out an individual from rank 1 and an individual from rank 2, and we can use our new static tournament selection method to get 2 resultant individuals. We then compare the resultant individual against the individual we're expecting using these assert calls. If any assert results in values that don't match, it will fail and it will provide a good error message. Awesome, so I know that was a lot to cover, and it's not really too specific to GAs, but considering I'm providing the code, I thought it was better that I explain why we made a lot of these changes. So the codebase is now in a lot better state if you end up using it as the basis for other projects that you might be working on. Now that we have all of that out of the way, let's get on to the other new exciting stuff. In the last video, I mentioned that we were going to use trip time as our second objective, which requires our roads to have speed limits. One thing I didn't mention was that while our road speed limits will be randomly assigned, longer roads are more likely to have higher speeds. This is done to both mimic real life and give better results. So going to our town helper class, we can see that we have a new method called populate speed limits. We first create a new random and we seed it with the value of 17. This ensures that if we use the default town positions, each run will have the same speed limits, and if we use random towns, we can reliably populate every road segment with a speed. The main loop is pretty basic here. We just loop over each of the towns and add the speed limit from it to every other town. Note that this does mean that the direction of our path impacts the time fitness. This is something that we might want to explore in a future video. Going back to the world class, you can see that not much has changed here from the previous videos. Inside our do generation loop, we still create the offspring in the exact same way as we did before. Once we have all of our individuals, we calculate their fitness, but instead of summing up the distances like we did before, we now call into a new helper method. Taking a look inside, the first thing that we're going to do is clear the rank and crowding distance from all individuals. As this will run one generation after another, all the parents from the previous generation all have ranks and crowding distances stored, but it is likely that the new individuals in the population would have changed one or both of these. Before we move on, consider our scenario. We have our distance axis that has values ranging from 10,000 to 16,000 pixels, while on the time axis we range from 220 seconds up to 356. Now this will change slightly with your initial population spawn, but the scales will be approximately correct. So if we have a small variance in distance, it will cause the individual to have a much larger crowding distance value than an individual which has had a large change in time. Yes, I'm sure this sounds very familiar. So before we continue, we need to normalize the fitness values for both objectives by dividing all individuals in the population by the fittest. Don't worry, we're not overriding the existing fitness values, we're just updating the normalized value that we're storing. We then loop over all of the individuals in the population. Any individual that is not dominated gets put into the first front. Now our not dominated check here is actually very simple, where we test the population to see if any individual is better on both axes. If so, the individual is dominated, so we return false. If we get to the end and no other individual dominates this individual, then we can return true. When we get to the end of this list, we have our first front. We can remove them and repeat the process. Great, so by the time we get to line 54, we know that every individual in our population has a rank. So we can group our individuals by rank and we can calculate the crowding distance for each individual in each front. This again is pretty straightforward. Because at any one time, we know we only have two objectives and we're looking at a single front, we can order the front by fitness in one objective and then use the resulting array as an ordered list of individuals from left to right. We then loop over each of the individuals in the front. If it is on either end of the front, we can give it an infinite crowding distance. If it isn't, we grab its left and right neighbor and we calculate the normalized distance, our new crowding distance. And there we have it. Every individual in the population has a rank and a crowding distance. Now back in the world class, we can grab the 100 most fit in the population by first ordering by rank ascending, then by crowding order descending. We have a small check here to ensure that we don't add duplicate individuals, but that's it. We have our top 100 individuals and our generation is complete. Let's go to our configuration class and set use random towns to true. Then let's hit run again and have another look at what we've got. Hitting spacebar, you can see the individuals on our map, we can see our Pareto fronts, and we can see our individuals improving. I don't know if this has been as exciting for you as it has been for me, but this has visually turned out way better than I could have hoped for. One thing that you've probably noticed is that we no longer have the convergence checks. So our GA will just keep running for 10,000 generations or whatever you've got your current maximum generations set to, or until we click stop. So that will be it for this one. The challenge question today is going to be the same as last week's, but hopefully now with a little more insight into how a real world problem would behave. How can we check for convergence in our multi-objective GA? Good luck, thanks for watching, and I'll see you in the next one.